Our second speaker for today is Ivo Vekemans from the Australian National University, where they are 90, how many percent vaccinated? 100%, wow. And Ivo is going to talk about Mackey and Tambara functors as G commutative monoids. Thank you, Ivo.
All right, g'day. I'm a PhD student with Vigilek Angelveit. I'm ostensibly an algebraic topologist, but I haven't seen any topology in like 2 years. I'm speaking from the unceded lands of the Ngunnawal and Ngambri people, and I'd like to pay my respects to elders past, present, and emerging. So, Mackey and Tambara functors. To my knowledge, these things sort of first cropped up in representation theory. My interest in them comes from equivariant homotopy theory. In a lot of contexts where a group G is acting on something, you have things that look like restriction, conjugation, induction, and tensor induction. And if you just take restriction and conjugation, then that gives you coefficient systems, which are due to Braudon, at least as far as I'm aware. If you include induction as well, or operations that look like these things, you get Mackey functors, which are due to Dress and Green. And finally, if you add in some multiplicative structure, like tensor induction, you get Tambara functors, which are due to Tambara, although they called them TNR functors. So these structures appear in representation theory and group cohomology, in algebraic K theory, in algebraic number theory, and where I care about them in equivariant homotopy theory. A bunch of examples, the Grothendieck group of a category of finitely generated KG modules, the green ring of finitely generated KG modules, that's the first two. And then we have cohomology, homology, and Tate cohomology of a group with coefficients in some ZG module U. And then here the algebraic K theory of ZG. This is the class group of the ring of integers for the fixed field FG, where G is a group of automorphisms of the number field F. Oh, and I don't have it here, but pi star of X for X a genuine G spectrum is ROG graded Mackey functor valued. It's an upgrade of homotopy groups. So at least in equivariant homotopy theory, you replace abelian groups as coefficients with Mackey functors, and you replace commutative rings as coefficients with Tambara functors. All right, so I'll start with the punchline, and the punchline is that Mackey functors and Tambara functors are G commutative monoids in the category of coefficient systems and the category of Mackey functors respectively. I'm basically not going to talk about Tambara functors because that was the thing I cut to make time. All right, so I should say what these objects are. So a semi-coefficient system over some G set X is a product preserving functor from the opposite category of the category of finite G sets over X. So this is some slice category. Interset. And so just quickly, the objects in this category are they're like a G set A equal to the map to X, and the morphisms are, so I want a morphism from A over X to B over X, but I'm in the opposite category, and so I actually am taking a map from B to A, and this triangle has to commute. Okay, some things about finite G sets. Coproduct, like any finite G set, breaks up into a coproduct of orbits like this. And because we're in the opposite category, the coproduct is the product, and so product preserving tells us this condition. And all maps of G sets, after you've sort of split it up into orbits, decompose into something that's a conjugation followed by a quotient. Now, for any G set, so here I'm suppressing that everything is over X. You just think about it being over a point. But all of this follows through if stuff is over a point, is over X or over a G set. So on any G set, the value that the coefficient system, semi-coefficient system takes is a monoid via the fold map and the map that you get, the map from the empty set. So from what's above, or at least from these two things really, a semi-coefficient system is entirely determined on what it does on the subcategory of orbits or transitive G sets. Now, a coefficient system is a semi-coefficient system that takes values in abelian groups. All right. So if we have, so as I said, we only need to say what conjugation does and what restriction does because all the maps break up into those things. So restriction is we rewrite restriction from H to K for the image of this quotient map when K is a subgroup of H. And then I've put down what the this CX map is conjugation. I'm not really going to talk about conjugation at all. It's always an isomorphism. All right, but first, now we have an example of a coefficient system, the Burnside coefficient system. So I should have said at the start, but I didn't because I'm flustered, that we should fix some finite group G. So G, this is only for finite groups. Some of this equivariant stuff translates over to compact Lie groups or pro-finite groups. I don't know much about that story. Anyway, on a given orbit, G mod H, the Burnside coefficient system takes the value of free abelian groups on isomorphism classes of H orbits. And restriction maps just come from restricting the action. So you started with a say in this example, the example I've written down here, as CP squared set, and then you just only remember the action of the CP subgroup in that group. And so this is an example of such a thing. A diagram like this is called a Lewis diagram. In this case, there isn't any conjugation actions, but when there are, they're sort of included like this. All right. Now, the linear category over a G set X, denoted as AGX, is a category. So its objects are finite G sets over X, and its morphisms between finite G sets are isomorphism classes of spans. So what's a span? A span is something like this. So this is a span from A to C. We're over X, so all the triangles have to commute. And I said isomorphism classes here, and that's really because there's something too categorical going on here, and we're just pretending it's not by just taking isomorphism classes. But if we suppress the X, then an isomorphism of spans is, so I have two spans between A and C, and an isomorphism of spans is just an isomorphism from B to D such that the triangles there commute. All right, and composition is defined by pullback. So if I have a span from A to C and a span from C to E, like so, I can take the pullback there, and then it's this span here. Okay. Now, what was the point of that? The point of that was that a semi-Mackey functor over a G set X is a product preserving functor from AGX It's a set. And it's a Mackey functor if it takes values in abelian groups. And something weird is happening with my pen, but oh well. That's illegible. Yeah. All right. So the category that was the source for our coefficient systems includes into this linear category, and it includes like this. So if we had a map in set GX op, it looked like this. And we include it by just putting that map onto the first leg of the span and putting the identity on the other side. And if you have a span, the two legs F and G, it is a composition of this span and this span. So in particular, that tells us the extra information of a Mackey functor as opposed to a coefficient system is these transfer maps that come from the right leg of the span. So I'm going to write TRHK. So if I have subgroups K and H and G, I'm going to write TRHK for the value that M takes on GK, GH. And again, this tells us everything because everything is still determined by what happens on orbits. And now I want to add so this gives me transfer maps in my Burnside-Mackey functor, and here it's H times over Ka, taking you from a K set to a H set. All right. Okay, and pullback in the category of G sets is something is a co-product of things where you take a representative for each. A representative for each double coset of K and J and H, and it has this form. Something is going on with my iPad. It's annoying. K intersect the conjugate of J by X. All right, so this is where the Mackey formula comes from, that you get from induction or restriction things, from composing an induction and a restriction. All right, now given a map of G sets, we get these functors. One is just post composition, and the other one is pullback. And now we can use these to define functors between coefficient systems over different G sets. So if I have a coefficient system over X, I can use this transfer functor to get a coefficient system over Y. And if I have a coefficient system over Y, I can use this restriction functor to get a coefficient system over X. All right. Now, under disjoint union and Cartesian product, and some extra stuff, the category of G sets over X is a rig category, which is to say disjoint union and Cartesian product look like addition and multiplication in a rig. Now, a module category C over a rig category is a functor from the rig category cross the monoidal category that you started with to the monoidal category, plus some natural isomorphisms and some coherence axioms. This is a definition that is going in my thesis, and as far as I'm aware, isn't anywhere else, but it's kind of like a really obvious thing to do. There are 19 coherence axioms, incidentally. It's very ugly. I don't know if I need all of them. Anyway, a coefficient systems over X is a module category over this, the maximal groupoid in the category of G sets over X, via this functor. So it sends a G set over X to the transfer of that map, the restriction of that map, and the coefficient system. So it takes this coefficient system over X to a coefficient system over A, then back to a coefficient system over X. All right, this is a module category. And the formalism that I'm using here isn't as clean as I want it to be, and it can be made better with two categorical stuff, but I'm still working on that. But for now, a G commutative monoid is an extension, is a coefficient system C with an extension from this groupoid to the whole category of G sets over X. So this is coefficient systems over XG, and I want to extend the functor that does this multiplication by a G set. All right. Now, a coherent G commutative monoid. So if I start with a coefficient system over a point, it's a coherent G commutative monoid if RQX. So if I use my restriction functor to go from coefficient systems over a point to coefficient systems over X via the only map that exists from X to Q, X to the point. If all of these are G commutative monoids and they agree, so that's the coherent part. They sort of agree under the transfer and restriction functors for any G set map. All right, and so how am I doing for time? Yeah. All right. So the punchline I wanted to get to is that there's a bijective correspondence between coherent G commutative monoids in coefficient systems over a point and G Mackey functors. So if we're given the direction back is just you forget the transfer maps. But if we're given a coherent G commutative monoid, we have these extensions. So the additional information from these extensions is that for any non-isomorphism of G sets over X, we get a map from the TRA restriction, so of C. And this thing, because if you compose the collapse to a point map, precompose it with any other map, you again just get a collapse to the point map, PA, QA, C to PB, QB, C. And in particular, when PB is the identity on X, so that B is X, this map goes from TP, A, QA, C to just the restriction to QXC. And this is a natural transformation because it's between coefficient systems, which are functors. And on the component for that natural transformation given by the identity on X, we can build this map from CA, which is the same thing as the restriction to A of C of A sitting over A by the identity, which is the same thing as TPA RQA C of the identity on X sitting over itself. And now we use the component of this natural transformation, which here gets us RQXC of the identity on X, which is just C on X. And then if we let phi be the map from GK to GH sitting over GH, then this is the transfer map TR HK. There's a similar story for Tambara functors. We replaced the transfer functor with a norm functor, and there's a theorem from Hoyer that the coherent G-commutative monoids in Mackey functors are the G Tambara functors. And thank you for your attention.